All right, let's just jump right into this. There's this profound, completely unsolved mystery in modern physics, and it sits right at the foundation of our reality. Today, we're diving into a highly engaging explainer based on a fascinating new research paper. This paper actually tries to bridge the gap between abstract recursive math and the hard empirical data of particle physics. If the patterns we're about to explore actually hold true, well, it's going to give us a radically different perspective on the subatomic world.
So, here's the big question. Why do the fundamental particles of our universe weigh what they do? You know, the standard model of particle physics is practically a crowning achievement of human intelligence. It works unbelievably well. But it has this massive glaring blind spot. It tells us how particles get their mass, like through the Higgs field, but it completely fails to explain the huge gaps, the hierarchical spacing, between the actual weights of these particles. There's literally no underlying first principle rule in the standard model that tells us what those numbers on the scale should actually be.
I mean, think about it. If you or I were designing a universe from scratch, we'd probably set up a neat, predictable, proportional system for mass, right? Like a sensible ladder of weights. But what we actually see in the data is just chaotic. It's this seemingly random scattering of particle weights spanning massive orders of magnitude, from the incredibly lightweight neutrino all the way up to the massively heavy top quark. There's just no obvious pattern. It honestly looks like the weights of our fundamental building blocks were just pulled out of a cosmic lottery.
Which brings us to Section 1, the Rule of Three, a phenomenological hypothesis. Let's see how this new paper proposes a wildly simple mathematical key to potentially sort out this cosmic chaos.
Now, to be clear right up front, this paper isn't trying to tear down the standard model. It's not trying to explain the actual physical why of particle mass. Instead, it uses what's called a phenomenological model. Basically, it's an exploratory framework. Think of it like, well, it's like figuring out the rhythm to a song before you actually know how to read the sheet music. They're testing out a trial structure just to see if these masses show some kind of non-random exponential clustering.
And the heart of their hypothesis is brilliantly simple. It's a discrete scaling sequence where a particle's mass is proportional to 3 raised to the power of n over 2. In this elegant little formula, n is just a simple integer, a whole number like 1, 3, or -4. Every time you change n, you take a multiplicative step. And the reason they chose base 3, a ternary scaling structure, is because ternary structures actually pop up all over the place in physics. It basically creates this recursive ladder across logarithmic mass space.
Okay, here is the absolute jaw-dropping moment. When researchers took this super simple logarithmic formula and checked it against the actual real-world masses of particles in the standard model, it yielded a normalized match of over 98%. Seriously, let that sink in for a second. A basic, recursive, exponential organization built purely on powers of 3 captures the broad mass distribution of our universe with staggering accuracy. No crazy, complex parameters, just simple whole numbers.
Let's move to Section 2, Testing the Scaling Ladder. We need to look at the empirical evidence and see how this recursive math actually holds up against the heaviest and lightest particles in existence. When you look at the data across the board, fermions, force-carrying bosons, even the Higgs field itself, this ternary structure achieves massive alignment. Look at this. An electron sits at an n state of 3, giving us a 98.3% match. The massive Z boson sits at 4, matching at 98.7%. The incredibly heavy top quark hits a whopping 99.7% match at an n of 1. And the Higgs boson aligns at -8 with a 98.6% match. We're talking about totally different categories of particles with massive weight gaps, all fitting neatly into this exact same exponential form. Now, you probably caught that negative number for the Higgs just now. By allowing both positive and negative integer states, this framework brilliantly spans wildly different regions of mass space. So you've got positive states clustering around 0, 1, 3, 4, 7, and 8, and then negative states hitting at -4, 7, 8, and 10. Mixing positive and negative indices like this works perfectly with the exponential formula. It lets the hierarchy scale way up and way down across multiple orders of mass, all while keeping that single, unified, recursive structure completely intact.
All right, Section 3, Hidden Triplet Patterns. Because, as we're about to see, the architecture of mass gets even weirder.
The mystery goes way deeper than just mass alignment. It turns out these integer assignments aren't just randomly scattered. They actually form repeated structural relationships.
When you group particles by their standard classifications, these incredible triplet configurations start to emerge. You see this 2+1 organizational pattern over and over, two related integers alongside a third offset value. We also see these cool partial symmetries, like +4 mirroring -4, or 8 and -8. It strongly suggests a coarse-grained recursive ordering, not just arbitrary math. And it's fascinating because this 2+1 setup mirrors other ternary patterns in physics, kind of like how protons and neutrons are built from paired up and down quark states.
But here's perhaps the most mind-bending detail of the whole explainer. The particles classified as stable and visible, we're talking about the up quark, the down quark, and the electron, the literal building blocks of everything you can see and touch in your everyday life, they are exclusively bounded by odd index structures, -7, +3, and +7. This odd index grouping doesn't just show up uniformly everywhere, it points to a highly specific asymmetric grouping specifically for the matter that constructs our visible universe. How crazy is that?
Which brings us to our final section, coincidence or universal law. Let's weigh what all this actually means. So, we've seen the 98% alignments, the hidden triplet architectures, the symmetries. But is this a deep structural truth of the cosmos or just a really elaborate, beautiful numerical coincidence? Well, the authors maintain strict scientific caution here, which is absolutely vital. They explicitly state they aren't claiming this scaling relation is fundamental or derived from established quantum field theory. They're not saying they broke the standard model, they're just pointing out that the mass hierarchy can be described by this recursive ladder. It doesn't tell us why the universe seems to love powers of 3 just yet. We need a lot more investigation to figure out if this is a true, emergent behavior of reality or just a statistical phantom. And that leaves us right on the cutting edge of the unknown. We've seen how a surprisingly simple exponential rule of 3 can neatly organize the chaotic weights of the universe's building blocks into a highly accurate ladder. So, what do you think? Is the reality of our universe actually built on a hidden mathematical fractal code? I'll leave you to ponder that incredible boundary between pure math and physics. Keep questioning and ask yourself what other coarse-grained secrets might be hiding right in plain sight within the data of the cosmos.